Hello everyone, today we start a new lecture on formal languages, automata and codes, and our seventh lecture will be devoted to the semirings and matrices. So what is a semirings? Semirings is some algebraic structure which has the following properties. A semiring K is a set equipped with operation which is denoted by plus and dot, which satisfying the following axioms. The first axioms: the set K is a commutative monoid for the binary operation addition plus with the natural element which denoted by 0. The set K is a monoid for the multiplication dot with the natural element denoted by 1. Multiplication is distributive on addition. What does it mean? This means the following. Just a moment. So if we have A, B, and C are element from K capital, then we have A dots B plus C is equal AB plus AC. And we have that B plus C dots A is equal B A plus C dots A. So also we have that 0 dot x is equal x dot 0 is equal 0 for all element x from K capital. So it's so obvious that every ring with a natural element is a semiring. And so very simple example of the ring is a set of real numbers. If we consider the set moment of real numbers, with two operation addition and multiplication of real numbers, then R with such operation is a ring. Moreover, such set with such operation is field, because every element of every real numbers under the operation plus under addition is a group, and for any non-zero element from the set of real numbers there exists the unique inverse. So for any x from R there exists the unique inverse element, such that only for elements which are distinct from 0. Also, when we consider the matrix 2 times 2 or the field R with usual addition and multiplication, that will be a ring, and hence we get a semiring. Good. Next. Other example of semirings as follows. The set of natural integer is a semiring, and so is the set of positive real numbers what we have. So if we consider the set of natural integer which consists of 0, 1, 2, and so on, yeah, 3, and so on. So, as usual, this set is closed is a commutative monoid with respect to the operation addition and operation, and the second operation multiplication of natural numbers, and we have that the axiom 1, 2, 3 holds, and no problem to show that 0 multiplied to any element of the natural number will be equal 0, yeah. And from the school course of mathematics, we know that the multiplication is distributive with respect to the operation addition of the set of real numbers. Also, if we consider the set of positive real numbers, we get similar result. So 0 is a natural element with respect to the operation addition, yeah, and the unit is a natural element with respect to the operation multiplication. Also, multiplication distributive with respect to the addition, and 0 as a number is a 0 element with respect to the multiplication, yeah. Good. The Boolean Semirings is composed of two elements, 0 and 1, and the axiom of the Boolean Semiring implies that 0 plus 0 is equal 0, 0 plus 1 is equal 1, and 1 plus 0 is equal 1. 0 multiply 1 is equal 1 multiply 0 is equal 0 multiply 0 is equal 0. And the Semiring is a Boolean Semiring B capital is specified by that 1 plus 1 is equal 1. It's a very interesting operation because if we consider any addition, 1 plus 1 is equal 0, we get the quotient field z by 2z. So the fields of the following numbers 0 and 1 but the Boolean, and in this so all our first three operations coincide with in our case, but we have 1 plus 1 is equal to 0. This operation and operation in the field z by 2z are distinct. Good. More generally, for any integer d greater or equal 0, we consider the set B capital D, which consists of 0, 1, so on, d plus 1. It becomes a Semiring for integer addition and multiplication defined for I, j from bd respectively by the following operation. So minimum 1 plus g or for d plus 1, and multiplication will be is equal minimal I multiply g, minimum of this element, and d plus 1. In particular, we have that B0 is a Boolean semi-ring, which was defined below, yeah? For any monoid M, the set P of M is a set of all subset of monoid M is a semi-ring for the operation of union and set product. So we have that we know that if we consider monoid M, yeah, then the monoid P of M consists all subset of monoid M, yeah, with usual operation A1 multiply A2. It consists of such product A1 small a2, where A1 belongs to A1 capital and A2 belongs A2 capital. So it's a multiplication operation, and the addition operation is the usual union. So, and I propose you the exercise 1, to show that P of M with such two operation, the additional operation, and such multiplication operation is a semi-ring. Next. A semi K capital is called ordered if it is given with a partial order satisfying the following properties. So I recall what is a partial order. If we have the relation, so if we have relation on k square, yeah, and this relation has the following property. The first property, x is equal or less from x for any x from x, yeah, from k, yeah. And the second antisymmetry, this is reflexivity, yeah, or reflexive relation. So if we have k, so in this moment, if we have a is less or equal b, and b is less or equal a, this implies this a is equal b, yeah, for ab from k. And the second, the transitivity, if a is less or equal b and b is less or equal c, this implies that a is less or equal c for abc from k. So such relation is called a partial order on a k, and k, the ordered pair k with the relation less or equal is called the partially ordered set or Bohr set. Good. And when semi-ring k satisfies the following properties. 0 is the smallest element of K capital, and the following implication holds. So if x is less or equal y, this implies that x plus z is equal or less y plus z for all z from K, and if x is less or equal y, this implies that x multiply z is less or equal yz, and z multiply x is equal or less z multiply y. So, and if the two property hold, we call Semiring K an ordered Semiring. So a simple example of ordered Semiring. So when we consider the Boolean rings, so which consists two elements, 1 and 0, yeah, we get that 0, everyone is less or equal 1, yeah, and all operation which were introducing below, yeah, preserve the order. So hence to condition 1 and 2 from the definition of the ordered Semirings hold. Also, I propose for you as exercise 2 to show that the set of natural numbers with usual operation multiplication and addition with usual order less or equal is an order set. And the second exercise to prove that we have same from for the set of positive real numbers with usual addition, multiplication, and with the usual order less or equal. So the usual order is defined in the following way, yeah, on the set of natural numbers or the set of positive real numbers. And other Semirings K capital is said to be complete if any subset AX capital of K capital it meets a least upper bound in K. It is a unique element K of K capital, such the following condition holds. The first condition, if x belongs to x, then x is equal or less k. Second, if x is equal or less k prime for all x from x capital, then k is equal or less k prime. So in future we shall write k is equal supremum of the set x capital, or k is equal supremum of such x small x, whereas x belongs to x capital, or we shall write in the following k is supremum of x, whereas x belongs to x capital. So the Semirings B capital or Semiring or the Boolean Semirings is complete, but the Semirings N and R plus are not complete. So I propose for you to prove this statement as exercise 4, yeah. So why is not complete? Because there are no least upper bound for all subset of n or r plus. So, but the Semiring n and r plus may be completed in the following way. If we put k is equal n or k is equal r plus, we put k italic k italic is equal k the union of the infinity, where infinity is such element which is not belongs to k capital. The operation of k capital are extended to k capital italic by setting for any x from k capital x plus infinity is equal infinity plus x is equal infinity. And second, if is not equal 0, then x multiply infinity is equal infinity multiply x is equal infinity. And third, infinity multiply infinity is equal infinity, and 0 multiply infinity is equal infinity multiply 0 is equal 0. And also we extend the order of k capital to italic k capital in the following way, by x is less or equal infinity for all small x from k capital. And the set italic k capital becomes totally ordered Semiring. So I propose you to prove that such k in two cases, when k is equal the set of natural numbers or the set of real numbers with the usual operation addition and multiplication with usual order, when we extend such Semiring the following way, proves that k italic k capital with such operation addition multiplication as such extended of the usual order of k capital is a complete order Semiring. So it's exercise 8. So next. So why this ring is complete? This ring is complete because any subset has an upper bound, yeah, and therefore it has a least upper bound. We defined by italic and capital is a set of natural numbers union infinity and r capital italic with star is the set of positive real numbers with infinity. To be complete Semirings, obtaining and applying the above construction to the Semiring n and r plus respectively. If k capital is complete Semiring, then the sum of an infinite family xi of element of k is defined by the following formula. This is supremum such finite sum, yeah. And in the case of the Semiring r capital italic plus, this gives a usual notion of summable family, a family xi of element of R capital plus is summable if the sum is finite, yeah? In particular, for a sequence x1 of element xn of elements of the complete semiring, we have that the sum xn is equal supremum such supremum, because any finite subset of the set of natural number is contained in some interval from 0 to n, yeah? Moreover, if I capital is a union of such I capital J is partitional of I capital, then we have that this sum is equal this double sum, yes, double sums. Let P and Q be two sets, and let K capital be a semiring. So P times Q matrix with the coefficients in K capital is a mapping from the Cartesian product P times Q to the semiring K. We denote indistinctly by that way or that way. The value of mapping M on the ordered pair. We also say that M is a K relation between P and Q. If P is equal Q, then we say that M is a K relation RQ. The set of all K relation between P and Q is denoted by the following K in the power P times Q. Let M belongs to correlation between P and Q. For any element of P capital, the row of index P of the mapping is denoted by MP star is an element of Q in K in power Q defined by the following formula. Similar, the column of the index Q of the mapping M is defined by M star Q. It is an element of K capital in power P capital. PQR be 3 set and let PQR be the 3 set and let K capital be a complete semiring for any M from K relation between P, Q and N from relation K relation of Q and R. The product of M and N is defined as the following element of K relation between P and R. Its value on PR is the following sum, yeah. And when P is equal Q is equal R, this we thus obtain a Schritt multiplication with term K relation between Q into a monoid. Yeah, and its identity is denoted by I Q or I capital Q. A monoid of K relation of our Q capital is some monoid of Q relation our Q. So what we have matrices, yeah. What we have here, so every such map we denote the mapping from such product here Okay, what does it mean? We get the matrix. We give the matrix. Here we have P elements. Here we have Q elements. Yeah. So the number is P capital, here Q, and PQ, and in the place PQ, yeah, here we can consider here having some MPQ, yeah. So in the place here is number P small, yeah. Here is Q small. There exists an element which we denote PQ in the usual case, yeah. And such operation is the usual operation of multiplication of matrix of the form PQ multiply matrix on QR, yeah, and we get in here matrix of the form P times R. Good. So we finish our lecture. I wish good luck. Goodbye.